In this video, I want to introduce the law of sines. I'm going to introduce the law of sines by stating it using this triangle. So we see consider the following triangle and labeled this way. And this is actually the way in which we'll label every triangle we ever meet from now on. So the vertices are going to be labeled with capital A, B's, and C's. The angle at vertex A is called alpha, the angle at vertex B is called beta, and then the angle at vertex C is called gamma. Our textbook will actually use A, B, and C to represent both the angle and the vertex. I like using the Greek letters for angles, so I'm going to do that in this video. And in a few other examples, I might just use A, B, and C so that we see a little bit of both. Across from vertex A and angle alpha, we have side little a. And so all of the things that are A's are across from each other. Vertex A, angle alpha, and then side A across from it. When I look at vertex B, that's where angle beta is, and then side little b is across from it. All of the B's are lined up across from each other. And finally, vertex C, angle gamma, and side little c. And so when I look at the vertices, I say those are capital letters, so I'm going to make that C a little more prominent with capital. And then the sides are all lowercase letters. And that way, if I write A, you know I'm talking about a vertex or an angle. And if I write little a, I'm talking about a side length. So it's here where we have to be careful to always use either capital letters or lowercase letters purposefully, because they have different meaning. The law of sines is a relationship between a side and the sine of the angle across from it. And so I can think about that ratio as a fraction, sine of alpha over a. And it turns out that ratio is always the same no matter the angle and side I choose. So sine of beta over b is equal to that same number. That's the sine of alpha over a. And if I look at the last angle, sine of gamma over c is that same number. And so when I look at this, it looks like kind of one long statement, but what I see are three separate equations we can then use in calculations. I can think of it as this equation, where sine of alpha over a is equal to sine of beta over b. And if I know any three parts of that equation, I could find the missing fourth part, right? If I know angle alpha, side A, and angle beta, I could find little b. Or if I know alpha, A, and b, I could find angle beta. And I could also think about it as this equation, where if I know any three of the four parts, I could find the missing fourth. And then finally, the equation of the bits on either side, sine alpha over A is equal to sine gamma over C. So I actually have three useful equations there. And because I'm dealing with ratios and thinking about fractions, I can flip them all upside down, and then those would all be equal to. And so it's like I get two different ways to think about the law of sines with that reciprocal in it. And that way, if I was looking for a missing side length, I'd probably let the side lengths be on top. And if I'm looking for a missing angle, I'd let the angles be on top. So here's the statement of the law of sines. Linked on our Moodle course, you're actually going to find a link that shows you a proof of the law of sines. But right now, I just want to use it to solve this triangle. Well, first of all, what does it mean to solve a triangle? To solve a triangle means to find all of the missing pieces. And so here I have a triangle that's listed that gives an angle alpha, an angle gamma, and a side B. Well, I can actually look up here and imagine that means I know side B, this angle, and this angle. And I can imagine that that should lead me to a solution. We'll draw a picture down here in a minute to help with that. So my job is to find all of the other stuff, the third missing angle and the two missing sides. That's what it means to solve a triangle. All right, well, let's think about drawing this particular situation. So I have a length B. B equals 59.5 inches. This will not be to scale. And if I think about knowing side B, I know angle beta should be across from it, right? Angle beta is always across from B. So there'll be some vertex up here that's labeled B, which means these two vertices on either side must be either A or C. Doesn't matter which one we label which right now, right? Because I could just imagine flipping it or looking at it from the other side of the board. And now I can imagine at A drawing a 46-degree angle. So I'm just going to imagine doing something that's like a 46-degree angle. From angle from vertex C, angle gamma is 63 degrees, so a steeper angle. And I can imagine that if I draw an angle here and I draw an angle there, they do have to cross somewhere, right? And so that I will get a solution here. And that's what's very nice. So let's see, I know this is alpha and that's 46 degrees. And this is gamma and that's 63 degrees. And when I look at what was given to me, I realize that I have an angle, the side in between them, the side in between two angles. So I have two angles and a side in between. I said that horribly. I have an angle, a side, and an angle. So what I'm really thinking about is I have two angles on either side of this 59.5 degree inch. And we actually refer to that as what we call an angle, side, angle. Sometimes we just write ASA. And that's telling me I know two angles and a side, but it's also telling me that side is between the two angles. So the order I write this kind of thing matters. That this says, not only do I know two angles, but I know the side in the middle of those two angles. All right, well, I hope you are looking at this and thinking to yourself, well, finding the third angle is the easiest of all of the things to find here. Because I know if I take all of the angles in a triangle, alpha, beta, and gamma, they have to add up to 180 degrees. So if I just do a little subtraction, I should be able to find that missing angle. And so let's see. From that total of 180 degrees, I need to take away 46, and I need to take away 63, leaving 71 degrees to be angle beta. So angle beta is 71 degrees. I found one of the three missing pieces, so I'm part of the way there. Side C is across from vertex C, and side A is over here. And now I need to find A and C. And I'm going to look at the law of sines, and I'm going to say, well, I definitely need to think about A over the sine of alpha. So I'm looking for A, and that's the sine of 46 degrees, is equal to, and now I know both beta and B. So I can use this piece to set equal to 59.5 over the sine of 71. I have a number and two other numbers over here. I have three pieces of the four things involved in that way of thinking about the law of sines where I'm just using these two pieces. I can definitely find the fourth. In fact, A is equal to sine of 46 degrees times 59.5 over the sine of 71 degrees. Just thinking about multiplying that to the other side. I'm going to make sure my handy TI-83 is in the degree mode. So let's see. The sine of 46 degrees times 59.5 over the sine of 71 degrees. And I find out that little a is approximately 45.3 inches. I'm just going to run to the first decimal place because I feel like it. A lot of problems will probably give me rounding instructions. That just seems right since B was rounded to one decimal place to follow suit here with A. And now we should find C. Well, I'm going to set it up the same way, where I'm going to think about saying, well, I need C over the sine of gamma, which is 63 degrees, and equal to, and I'm still going to look at what was given to me. And the reason I'm going to use that is because I haven't rounded any of that. 59.5 was given to me, and I didn't have to round that 71 degrees when I found it. I guess technically I could use A and alpha, but I've rounded that, and so I'd lose precision and accuracy there. So this is going to give me the best possible answer. And so let's see. I'm going to do the same thing, where I'm going to take that 59.5 over the sine of 71 and multiply it by sine of 63 degrees. And I've run out of space here, and I feel confident in this calculation since I've done it once, so I'm just going to let my calculator do the work. And I find that C is 56.1 inches. So I found A, C, and we had already found angle beta. And we've now solved this triangle using the law of sines. Angle-side angles always have exactly one solution. And you can think about having a side, rotating an angle, and drawing a ray that goes out infinitely. And any angle I put over here that's not, parallel to it will cross it somewhere and give me that solution. That's very nice about the angle-side angles. I could also just imagine a case where I have an angle side, right? I know two angles in a side, but not the angle between them. But one of the things that we kind of discovered in this problem was if I know two angles, I automatically know the third, right? So if I know these two angles, it's like for free, I get to know the other angle just by subtracting from 180, which means there's really no difference between an angle side angle and an angle angle side. Because after I find this 71 degree angle, that's an angle angle and a side, or an angle angle and a side, and if I wrote that 71 degrees down first, we could have found either of these two. Because anytime you know all three angles in a triangle, anytime you know two angles in a triangle, you get the third one for free. In the next video, I'm going to solve one of these where we have an angle angle side instead of a angle side angle, and we'll find out that case is exactly the same.